Hello guys, and welcome to the third video on this Laplace transform series from finite time signals to the frequency domain. Now we're going to focus on another kind of signal. We're going to try to find the Laplace transform of a signal like this. So the question is that we should determine the Laplace transform of this unit pulse or this square wave. So determine the Laplace transform of the signal below. So let's just jump into the answer right away. So solution. Now to find the Laplace transform of this unit pulse signal represented like this, first and foremostly you need to do what? Define the properties of this unit pulse signal, and there's no other way to do that than to use your piecewise continuous pattern or using your branched pattern. Now identify what is happening. So what are the branches of this function? So from 0 to 1 we can see that the function has a constant value of 1, whereas from 1 to infinity, okay, so infinity, the function is resting on a value of 0 like this. So from 1 to infinity, the function is resting on 0. So this makes us to define our function as x of t is 1 from 0 to 1, and x of t is 0 for all values of t greater than 1. Now I established in the sawtooth video before this one that this expression is still the same thing as you writing from 1 to infinity. Is that okay? So this is just a short form of writing it like this. So anyone you want to write, no problem. So the reason we write it like this is so that when we are defining our Laplace transform, okay, our Laplace transform, the Laplace transform of this signal x of t is taken to be the integral from 0 to infinity. And you now have your x of t multiplied by the term exponential minus st dt. So s is the Laplace variable. Remember, it's a complex number, and in another video I'll explain more about what this s entail. Now you have to follow the next step to separate your integral according to the branches of your function. So you break this integral down according to the branches, and where are the branches? Our function starts from 0 to 1 and it behaves in one particular way, having a value of 1. Then it continues from 1 to infinity and it behaves in a particular way, having a value of 0. So that's exactly what we're going to do. We're going to break the integral into 0 to 1 first, okay, according to this first branch, 0 to 1. Then we'll put our x of t exponential minus st dt, and you now have plus. Then the second branch is from 1 to infinity, and you put your x of t exponential minus st dt. Okay, so this Laplace transform of x of t becomes x of s. Anytime you take the Laplace transform of a time domain function, you convert it to a frequency domain function, x of s. X of s is a frequency domain function because s is equal to omega, okay, sorry, alpha plus omega t like this. So that's the value of this complex number, or j omega t, sorry. So s is equal to alpha plus j omega t. So that's the value of s. So that's why we call it frequency domain. The reason why you call the Laplace variable frequency domain is because of this parameter here. This is omega. This is your angular frequency, okay, equal to 2 pi f. So we are converting a signal from time domain to frequency domain, and that's the meaning of this s variable over here. So we'll learn more about that one later on. Now just take it that whenever you take the Laplace transform of x of t, you convert it to capital letter x of s, and this is what we have. Next thing is to replace this x of t with the behavior from 0 to 1, which we recorded as 1 dot exponential minus st dt. then plus the integral from 1 to infinity. The behavior between 1 and infinity of this x of t, according to the branch function, is that it is 0 between 1 and infinity. So you replace as 0 dot exponential minus st dt. As usual, this place is going to evaluate to 0. So you don't need to focus on this second part of integration. You're just focusing on this part. So your x of s is the integral between 0 and 1 exponential minus st dt. So if you evaluate this integral, x of s will be evaluating this, the integral of, remember, integral of exponential at dt is the same thing as exponential at over a. So applying that to this one, taking a as minus s, we'll have that the integral of exponential minus st dt will be exponential minus st all over minus s. So you evaluate it within your definite integral limits from 0 to 1. So I'm going to show you a trick to apply to this kind of integrals. So whenever you have something like this minus sign can be transferred to the limits or to this definite integral part and see what will happen. So the minus sign has gone. So where did it go? It has reversed the polarity of your definite integral. So the effect of minus signs on definite integral is that minus sign can reverse the polarity of definite integral. So if you want to find out how minus sign reverse the polarity of definite integral, subscribe to my channel, like my videos, and I'll show you how it works. But I believe you know how it works, so it's not so difficult. So let's continue. So it's a new skill you should learn. So I don't like seeing minus signs. That's why I usually transfer the minus signs to the definite integral and use it to, reverse the polarity. So x of s, applying this definite integral, will have definite integral when t is 0 minus the integral minus when t is 1. Okay, so applying this over here, you have minus s dot 0 all over s minus exponential minus s dot 1 all over s. So this simply leads us to, this an x of s, capital letter x of s is equal to exponential minus s dot 0 is 0, and this is eventually what? 1. So exponential 0 is 1 all over s minus s times 1 is still minus s all over s. So when you factor out you s 1 over s, you get 1 over s bracket 1 minus exponential minus s. So the Laplace transform of our unit pulse signal is 1 over s bracket 1 minus exponential minus s. Okay, so you leave it here. So I hope you understood how we got up to this point. So if you do, don't forget to like this video, subscribe, and try to go through it by solving it on your own, following all the principles I taught you, especially this trick here where the minus sign can reverse the polarity of a definite integral. Then yeah, we're good to go. So see you in the next video. We're going to solve another square wave signal that has two particular squares this time around instead of just one. If you want to see how I'm going to get the answer to that video, make sure you hit on the notification bell to stay updated, and you're going to see the video in the playlist. So thank you very much for watching and stay blessed.